Hello, this is Professor David Clough again with you, and we're moving on to the third boot camp for MATLAB. This particular one, as shown here, will focus on the modeling and simulation of two different chemical reactors that each has somewhat different characteristics from the other. And one of the primary purposes of this third boot camp is what we would describe as capstone, in that the models that we're dealing with here are more complex, and they bring together many of the techniques that we have introduced in the previous two MATLAB boot camps. Also, since they are more complex, we are illustrating methods for approaching the modeling of more complicated processes, keeping the models organized, using modular techniques, etc. So the first of these models has to do with a very well-known large-scale chemical process, and that is the production of ammonia in a reactor packed with catalyst pellets, and modeling it as plug flow through the packed bed. This slide just gives you an idea of the scale of the process that we're talking about. On the left, we show a reactor before installation, and with the base of the reactor on the left here. And you can see its size relative to a person standing over here at the left of the photo. And on the right, it shows an ammonia reactor installed vertically, and notes that the world production is 180 million metric tons per year. Now, it turns out that the reaction kinetics for our main reaction, that is combining nitrogen and hydrogen to produce ammonia, the reaction kinetics are not terribly complex. It is a reaction that has a forward and a reverse path, so we need the kinetics for both, and they are described here with appropriate parameters and units. We are using, since this is a gas phase reaction at high pressure, we are using partial pressures for our rate expression. The rate parameters described by the Arrhenius expression, and the frequency factor and activation energy with specific units are provided here. The reverse reaction, again, is just first order in ammonia, and again, the parameters of that are provided. All right, these are readily available from the literature. So our concept here is that we have a feed stream of nitrogen and hydrogen. Eventually, as we model the reactor, there will be a couple of inert gases that are carried along through the reactor but do not participate in the reaction. And then the reactor, we're giving it a cylindrical geometry with a certain length and inside diameter. And we have feed flows, and we have product flows, which include unreacted nitrogen and hydrogen, because this reaction is not carried to completion. in the reactor itself because the reverse reaction becomes more prominent as you go through the reactor and prevents complete conversion. So we create balances based on our molar flows, and the primary example here is the change in the flow of nitrogen with respect to volume, given by minus the consumption plus the reverse reaction, and then times the void fraction of the packed bed, all right? And that's the epsilon factor. And we note some geometric relationships here in terms of the differential of volume with respect to the differential of length, and the area being the area void of empty area, as if catalyst pellets were not there. And then once we have this differential relationship, we don't need to write differential relationships for the hydrogen or ammonia, because they are available from reaction stoichiometry as shown in these two equations here. So this gives us the essentially a fairly simple material balance for the reactor. But as we move on and consider the energy balance and the fluid flow or momentum balance, things become more complicated. So the overall energy balance is a conservation of enthalpy rate, and that is given by this equation here, where we've got the sum of the flows of the components and their individual enthalpies equal to zero by conservation of energy. And then if we are able to assume constant heat capacity, it then allows us to simplify this and have instead a differential in terms of temperature with respect to volume. And the denominator here is the part that is able to be removed from the derivative on the left-hand side. And then we can deal with the rates of reaction and the corresponding heat of reaction in order to account for the enthalpy changes as we go through the reaction. And the one thing we note here is that the heat of reaction is the function of temperature, as we would expect, but also a function of pressure. And the reason that this needs to be kept in mind is that this reaction is run at very high pressure, 150 atmospheres, so the effect of pressure on enthalpy can be significant. So if we take an enthalpy expression in terms of a component, then we can account for its enthalpy based on changes from reference temperature and pressure by the temperature effect with heat capacity, and then the pressure effect given this particular expression with a differential with pressure. And then we've got an initial or a feed enthalpy here on the right. And these represent the changes from the feed enthalpy. And then we can look at each one of these terms. This one here quite often is simplified by using an average heat capacity as a function of the temperature. And that's an integrated version. That is often done, and we will do that. And then we need to deal with how do we come up with this pressure term, and the ways that can be handled is based on an equation of state which has to be one that models the non-ideal situation with the gas because of the elevated pressure. And we can do that analytically, or if we have PVT data, we can carry out that integral based on data, or we can use something called the generalized Pitzer correlation. So this gives you an idea of how we start breaking down the energy balance, all right? And so we'll come back to that in a moment here, but we're going to go along and look at momentum balance in terms of modeling the pressure drop through a packed bed. And a typical method for doing this is something called the Ergun equation, which you may have run into in your past experience with fluid mechanics. And this is a way to model the pressure drop through a packed bed, the overall pressure drop, and then if we differentiate this in terms of pressure with respect to volume, we can come up with a differential form of the Ergun equation and use this to account for pressure drop as we go through the reactor. And all of the terms in this are denoted here in the nomenclature. And the one thing to take note of is this G naught is the mass flow rate per unit cross-sectional area of empty bed. And that is, by conservation of mass, is constant with V. So that becomes a constant in this equation. And many of the other parameters are constant, as you can see. All right, one thing that isn't constant is the density of the gas flowing through. So we have to deal with that. And possibly the viscosity of the gas as it changes in temperature and pressure. So that's a bit on pressure drop, and let's expand that a little bit here and indicate that our fluid density can be expressed in terms of average molecular weight over specific volume, all right? And we can obtain the specific volume from an equation of state. And here we're using the Peng-Robinson equation of state, and that it is denoted here. And the question that we have to answer is that you may have dealt with Peng-Robinson before in terms of a single component, but we have to deal with the parameters for the equation as mixture coefficients depending on the composition of the gas. And then we might make note is that we could always try to compute the density based on the ideal gas law, but that turns out to involve an error of at least 20% at our operating pressure, and that's why it's indicated to go with a more complete equation of state. So let's talk a little bit about these mixture coefficients. You may have seen the expressions before for the individual components based on critical temperature and pressure, this factor for component I based on the acentric factor, which comes into the expression here. These A and B give individual coefficients, and then we need to know how to come up with our mixture coefficients. And this is indicated in the expressions here, where we form a matrix, and that is shown in vector matrix form here, and is shown here, shown by these particular mixture coefficients, all right, times the multiplication of the A coefficients for the individual components. And then the B mixture coefficient can be obtained quite simply. So we then have that the A mixture coefficient is given by this particular quadratic form of our composition times this Q matrix times the composition. So that's how we come up with the mixture coefficients. So you can see this getting a little bit complicated, and we want to see how we can come up with the model, or an idea of how to formulate the model for our reactors. So we're going to start with that simplified version where we're assuming constant heat capacity, and we're going to organize the model in what we call an information flow diagram as shown on this slide. And this is a very good way to illustrate the model and see how all of the various calculations sort of hold together to provide a consistent approach. So the first thing we come back to is our one differential equation here for the material balance. And then we assume that we have a numerical method with some help from MATLAB that will integrate this equation and will provide, as we go along, the flows of nitrogen. Once we have those, we can go into our two stoichiometric relationships and provide the flows of hydrogen and ammonia. And then we can use the three of these in order to come up with the total molar flow rate, all right? And then we have the total molar flow rate, and we are then getting our partial pressures by taking individual over total multiplying by total pressure. Now here we're assuming for the simplified model that there's not enough pressure drop through the bed to be of concern, so we're assuming that the bed is relatively close to the feed pressure. We'll generalize that with a full model later on. And then down here we have our differential equation for temperature, and this is the one where we assumed constant heat capacity, and we're able to compute the heat of reaction based on temperature and pressure, where now pressure is going to be constant. So, and then once we have the temperature, which is required to specify its derivative, we can bring that around to the Arrhenius rate parameters, and then those with the partial pressures give us the rates, and that then ties the whole model together. So what we want to do is see how we take all of this and put it together into a model using MATLAB. So I'm going to pop over to MATLAB's editor now. First, let me come to MATLAB here, and then bring up the editor on top of the command window so we can see the workspace. And I'm going to open a file that is called Ammonia PBR Simplified. Okay, so that we're going to now see how we move through somewhat systematically, again establishing our basic data and then setting our operating conditions, and then moving forward to solve the model, mainly solving those two differential equations. So you can see here that we have a gas law constant, we set our molecular weights, and then we set parameters for heat capacity. And here, these have been developed actually by making a fit of predictions from HISIS at 150 atmospheres. And these are coefficients of a polynomial that is used to compute the heat capacity of each of our constituents. And you'll notice there are 5 constituents here because we have two inerts. And then for our assumption of constant heat capacity, we assume a mid-range temperature, all right? And we calculate the heat capacities for that particular temperature, all right? And this makes use of a function called heat cap. So if we'd like to see that, we can open it in heat cap. And we come back here, and what we see is heat cap takes an argument first, which is a component index, all right? And this then becomes the row that gets the coefficients that we need for that particular component. And 1, 2, 3, 4, 5 are the 5 columns in that array, the CP coef array that comes through as an argument. Now you'll notice here that the argument T is actually in Celsius, and then we convert that to kelvins, and we scale it by 1,000 to put it into this particular polynomial formula. That is the typical way that the heat capacity is computed on a resource like NIST, and so that's why we approach it in that way. One thing that I'm going to note right away is that the heat that the T mid here is actually at 350 degrees C. So that's just a change in the comment that you will see when you look at your PowerPoint slides. And when you open the file, I'm making a little fix here. And then we move down and we do reaction kinetics, and we have our constants for the forward reaction, Arrhenius constants for the reverse reaction. Then we specify our reactor in terms of diameter and length, and we then make associated dimensional calculations for cross-sectional area and volume. Then we move on and provide the diameter of a catalyst particle as a millimeter, and we provide a void fraction, all right, as basic data. The dP is required if and when we go to the Ergun equation. Then we come to operating conditions, so we set our feed rates, and you'll notice we also have significant feed rates of argon and methane, and this is to make this more realistic to an actual industrial reactor. And we put our feed pressure at 150 atmospheres and the feed temperature at 270 degrees C. So that is ends our operating conditions. We come down and we say that what are our initial conditions to solve our model. And the initial conditions, we have our feed rate for nitrogen, hydrogen, and ammonia, and our temperature. So we have 4 variables that we're solving for, and we note that the temperature and the feed of nitrogen are both governed by differential equations, but hydrogen and ammonia are governed by the stoichiometric relationships, which are algebraic. So we're going to solve this as a differential algebraic system, and that requires us to use the ODE 15S integrator, not ODE 45, in MATLAB. And we create a mass matrix, as we have done before in Bootcamp 2, where on the diagonal, we place a 1 where we have differential equations, nitrogen and temperature, and we leave zeros where we have algebraic relationships set equal to 0 for hydrogen and ammonia. Then we create a V-span for volume between 0 and the total volume of the reactor, and we say we would like 200 points. We want the solution to stop and give us results at 200 evenly spaced points. And then we move on and we set up to solve the differential equations. Now here, because we have to share many parameters from this main script over to our script which computes our derivatives and equations, we need to create an anonymous function as we did before. And here we say that we've got volume V as the independent variable and Y as an array of our 4 variables that we're solving for, both differential and algebraic, and then we relate that to a function called PBR simplified, which includes the V and the Y, but then includes a very long list of parameters that we have set here that we now want to be made available to PBR simplified. And this we have done before. We set our mass matrix as M, and then we solve the equations using ODE 15S with our anonymous function, our V-span, where we stop, get solutions, our initial conditions, and our options, which provide the mass matrix. We'll come back to this to show you how we deal with the results in a moment, but let's take a look at our PBR simplified routine. So we'll come and we'll open that and we'll look for PBR simplified. Here it is, and open that. And this is the routine that essentially computes our derivatives and our algebraic relationships. You'll notice that it has the same list of arguments that we had in our anonymous function definition. So now all of these variables, feed N2 to heat capacity, methane, are all available to this routine. So what we do for starters is we take our current values of our dependent variables, and we are unpacking the 4 of them just into variable names which are more familiar to us: mass, molar flows, and temperature. Just like our model information flow diagram, we sort of follow that now, and we create the calculations of our model, the total flows, the partial pressures. Now with the partial pressures in hand, we can calculate our reaction rates, all right? Our reaction rates using the temperature and the Arrhenius expressions and our partial pressures. And then we come down and we specify our variables, the rate of change of nitrogen with respect to volume. That's our differential equation there. And then we have our 2 stoichiometric requirements, both set equal to 0. And then we come down and we say we have to compute the heat of reaction. And because we're going to use that down here in our energy balance, yielding the derivative of temperature with respect to volume. You'll notice that takes advantage of a function called HTRXNP. So let's peek at that. And this is what goes through and calculates for us all of the requirements in order to come up with the heat of reaction. And here again, we introduce a gas law constant. We have these 5 parameters in order to get a temperature-based heat of reaction, all right? And this essentially is modeled based on data for heat of reaction at different temperatures. And then we establish our critical temperatures and pressures and our omega variable, reduced temperature, and convert our pressure over to kPa for the purposes of the calculation. And then we go through the calculation of our B coefficients. And then finally, we calculate the heat of reaction based on the H variable and the associated stoichiometric relationships for each of those H calculations. And this is, H is an array, so we associate that with stoichiometric coefficients based on the reaction. So this provides for us our heat of reaction. So let's come back. And then we've got our change in temperature. And here it's exactly what we had in our model, the difference in the reaction rates, the heat of reaction, epsilon, and then divided by the various molar flow rates times their heat capacities. And then we return this as the both derivatives and algebraic expressions back over to our ODE 15S routine, which solves the equations. And then we unpack the solution that we get at the end, columns 1, 2, and 3, and column 4 for temperature. For all of those 200 points, we calculate the conversion, all right, in percent. Like to see a plot of that. And then we come along and we create a series of plots, a temperature profile, and you've seen before how to set up plotting or plots, molar flows profile, and here we include a legend because we've got our 3 flows, and then we have our conversion profile down here in our 3rd figure, and at the end we save the solution in a text file for use later on, and you'll see how we use that. So that is the nature of the code that completes our model. Let's pop back over to the slides and just see that that's all present there for you. It takes several slides, but this is the the main script, Ammonia PBR simplified, all the way to the end. And then we have the function that computes our derivatives and algebraic requirements. And then we've got our supporting functions. And then we'll come back and run the model so you can see how it works. So we come back over here and let us get our command window back. And then we're going to run our model, all right? Okay, so what it does is it gives us our conversion profile. And what you will note is that for reactor volume, we have a total of 8-ish cubic meters, a little more than 7 cubic meters of reactor volume. And we get close to that, and it appears that the reactor reaction has slowed to a halt. And it's looking that it's at about 22 to 23% conversion. And this is typical of ammonia, and it's why for the ammonia process, you take the product stream from the reactor and you condense out the ammonia by cooling it, and then the remaining nitrogen and hydrogen are recycled for another pass through the reactor. And then you also have to deal with the inerts and create a purge stream so that inerts don't build up in the process. But that's just more of a general comment. We have that, and then we have our molar flow profiles. So we can see our ammonia coming up, and this is in terms of kilomoles per hour. And then we see our nitrogen being consumed and our hydrogen being consumed. And that shows you also that that conversion is pretty much stopped by the time we hit about 6.5 cubic meters. And then we have our temperature profile, which shows the exothermic nature of the reaction, where it starts at about 270 degrees C and ends up at about 420 degrees C. So those are the results. Okay, what we're going to do here is illustrate a typical way to debug a model like this if you're having results which are incorrect as you first try to run it. So I'm going to come over to the routine that computes the derivatives and algebraic expressions. I'm coming down to the last line, and I'm going to click on the line number, and that creates a breakpoint. So the first time that this routine is accessed, the very first time, which will be with initial conditions, it's going to stop there so that we can take a look at all the variables and we can see if things make sense. So if I come back here to the main script and run the main script, then it stops immediately on this line. And over in the workspace, we can take a look at all of the values that have been computed. Which down here, we can take a look at the partial pressures to see if that makes sense. We can come down and we can look at the Y values by opening up the matrix and see that these are the derivatives that we have, or for the first and the third are the derivatives that we have. And then we've got the intermediate two are the results of evaluating the algebraic expressions. So we can look at that, and then we can decide if we need, if there are problems, we need to fix it. And then at that point, we can click the stop button up here to stop execution. And then when we don't want the breakpoint anymore, we can right-click it and say clear the breakpoint, and it's gone. And so you can place breakpoints anywhere in your code in order to stop and then take a look at values. The other thing, of course, that you can do is that you can put a breakpoint, for instance, at the top of this particular routine up here. And then you can come back and you can start the simulation, run the model again, and it stops here. And then I should have cleared the workspace, but what you can do is that you can single step it by hitting the F10 key or this button up here, and it will start moving through. And as it moves through, you can take a look in the workspace and see what the values are. So let's stop that, and then I'll remove that breakpoint just by clicking on it. So I wanted to mention that, And then we come back over to our slides here. And this shows the results, and also on the slide I added here for the conversion what the actual conversion value was as displayed over in the command window at 21.8%. So at that point, what we want to take a look at now is, now that we've done that, is how would we approach solving the full model and not the simplified model. So let's move on to that. And as you'll see, it requires a different approach and brings into play other techniques that we have seen before. So here is the full model. And in this particular case, we have two differential equations, one in terms of our flow, just of nitrogen, just as before, and then we've got another one which is solving the Ergun equation to provide the pressure, so that the full model allows for us to have the pressure vary as the flow goes through the reactor, and due to friction, the pressure actually reduces somewhat. And then the upper part of the model here is very much the same as we had before, but then we get to where we were having a differential equation for temperature before, and now we don't have that anymore because we're not assuming constant heat capacity. So we've got an enthalpy balance where the initial enthalpy is conserved, and we have to solve this equation here, which is a nonlinear algebraic relationship, and solve it so that this equation is satisfied, and then that produces our temperature. So that gives us the need for solving an algebraic relationship. Now, the other thing that's new down here is that we calculate an average molecular weight, and then the Ergun equation requires a couple of live variables that we have to compute, one being the density and the other being the viscosity. The rest of these are constant parameters, so we don't need to be computing them on the fly. The density we've shown before is the average molecular weight from here divided by the specific volume, and the specific volume we can get by solving the Peng-Robinson equation of state, which is shown here, all right? And we need to solve that for specific volume. The one thing I'm noticing here, this initial V with the tilde over it needs to be squared, and I will correct that because this is a cubic equation in V. And then when we want to get the viscosity, one technique to do that is to use the inherent viscosity, which is relatively constant, and to compute from that, the intrinsic viscosity, to compute from that using the density, the dynamic viscosity, which we can put into the equation there. So again, this is more complicated than the simplified model, and so we'll go through and we'll show you how we put that together now. So let's come back over to our command window and to our editor, and let's remove the routines having to do with the simplified model, and let's open a file called Ammonia PBR Simulation Full Model. Here it is, okay. And the front end of the code here looks very similar to what we had in our previous model, right? Similar. And so we can come down through here. This is all the same, essentially. And then we calculate, we have a couple of additional parameters here, kinematic viscosity, which we get from HYSYS as a constant parameter, and then we do our initial mass flux, all right, and then we compute the G0 value for the Ergun equation, which is going to be constant. And then we have initial conditions, which are now somewhat different. We have our feed temperature, and we have our initial enthalpy value, which we compute, all right, given our feeds. And that's the one from our model here, the H0 value that we need in order to solve this for temperature. And then we set our initial conditions, somewhat different now because we've got our differential equation for nitrogen, we've got our two stoichiometric relationships, we've got our differential equation for pressure, and then we have our H0 and our feed temperature initial values, all right? We construct our mass matrix here, all right? And then come down and very much as before, set this up, but now this is PBR-SYS full model, and it actually includes more constants that we need to pass through, and then we solve this particular anonymous function for our solutions. So let's come over to PBR-SYS full model, and let's open that. So this is the routine that computes the derivatives and algebraic expressions for us. The front end of this, the same idea, is to unpack the y-dependent variables into the various values, all right, and the variable names that are familiar to us. Just as before, the total flow and the partial pressure and the rate, the reaction rates, and then we start working on our derivative and algebraic values. The first one here is our mole balance, which we've seen before, and then our two stoichiometric relationships. And then we come down here and we deal with the Ergun equation to get the differential of pressure, and that's more complicated, but it follows, going way back to the slides, to come up with the calculations using our binary coefficients. And in order to do this, we also need what is the specific volume of the gas. That's the V with the tilde over it. So let's go see how we get that by opening the functions SPECVOL. And you'll see why it's so important here to break this down and modularize it into separate, smaller functions that we can look at and we can debug separately. If we try to put all of this into a single code, it's going to be unmanageable. So what we're dealing with here essentially is solving the Peng-Robinson equation for the specific volume. These are all the initial parameters, and then we go into a while loop, and we use the modification of Newton's method, which is the modified secant method, in order to solve for the specific volume using the Peng-Robinson equation, all right, which we'll look at in a moment. And we use a slight perturbation of the volume in order to get an approximation to the derivative, all right, of the equation with respect to v. And so if I look at the PR routine now, this is fairly short, but what it does is it computes for us the Peng-Robinson equation set equal to 0, which we will achieve 0 when we have the correct value of the specific volume. And remember, I mentioned a correction on the slide of a v tilde going to a v tilde squared, and that's shown here where you've got the v squared. And I will correct that on the slide. So that comes back, gets us the specific volume. Once we have the specific volume down here, then we can get the density of the gas, and we can get the gas viscosity from the kinematic viscosity times the density, and then we can get our derivative of the for the pressure with respect to volume. And then the final down here is to find our heat of reaction just as we did before. And then we have an algebraic equation in order to find the temperature, all right? And that uses a routine called find T. So if we open that, here it is. And again, this is a routine that uses that same modified secant method to solve the enthalpy balance for temperature. And that is this one here, to solve that for temperature. And using the same modified secant method where we perturb the temperature by 1/10 of a degree and then have an estimate for the derivative in the bottom of the Newton's method type formula, with the delta here being in the top. And this will find our temperature for us, and it uses something called FH, again modularized, and FH calculates our enthalpy balance, all right, which we will have equal to 0 when we've got the right temperature. So this is just coming from our equation for the enthalpy balance, okay? So that's how that works, and we come back over to this. That gets us our final energy balance, all right? And which we set here in order to get that in terms of an actual H value differential energy balance using the heat of reaction. So that completes that. We come back to our full model here, and we are able, I believe, to run the full model. And it gives us our conversion profile, just as we saw before. And then very similar looking molar flow profiles. And then we also get a pressure profile now, where the pressure is dropping from 150 atmospheres roughly down to 144. So that's a 6 atmosphere drop, all right, and on 150. So we can consider if that is significant enough that we should include the accounting for that with the Ergun equation, okay? So we've got that, and it shows our temperature profile. So one thing that you'll notice as we unpack our results and make our plots just like before, that we saved the model results in values in a text model, and we want these values to be saved in a text file. And then what we are able to do later, having done that, is come in and open a script which is called model comparison. And here what we do is we load our results from the full model and from the simplified model that we saved from before. And we create some handy variables for the full model using a lowercase f here, and then similar variables for the simplified model, again using variable names with lowercase s. And then we can create a couple of plots that illustrate for us the comparison between our two models. So if we run that, it shows the full model and simplified model here. And you can look at these and you can say the results are fairly close, but the full model conversion is less than the simplified model. And as going down the reactor, it takes longer before it approaches the equilibrium value toward the end of the reactor. So that's one. And then the other shows the temperature comparison, and it shows the temperature not quite reaching the temperature of the simplified model. So we compare these two models, and then we can decide more or less whether it was worth it to go on to the complexity of the full model or not, all right? And there are intermediate models that might be considered too, where we consider the simplified model, but we add in the air gun equation to allow for the pressure to change, but still keep the heat capacities constant, all right, at a midpoint value. So let's come back to our slides. And again, this is the code for the full model that we looked through before, very similar, except now it has some additional information that's required for the air gun equation. And we end up solving it at the bottom here with ODE 15S, unpacking the solution and making our plots, and then at the end saving our variables for that comparison script. This is the full model routine that computes all the derivatives, and that ends at this point here. And then we have our supporting functions for heat capacity, heat of reaction accounting for pressure, specific volume, Peng-Robinson equation of state, find T and find H, and then we have our results, all right? So that's about it for that. This is the script that handles the model comparison, and these are the graphs for the model comparison, which is sort of an interesting and an important thing to do to help you evaluate whether your simplified model is okay or not. So that completes our study of the ammonia synthesis reactor. I realize that the complexity here may be a bit much for you, but the idea that we want to put forward here is that if you have some type of a similar situation to approach, these are the kind of considerations that you have to put together, decide on what assumptions you make, develop your basic data, your model equations, operating conditions, organize the model into an information flow diagram, and then use that as a basis to convert it over to MATLAB code. debug the MATLAB code, and then work with it, generate results, make changes as you see need to study the behavior of the process that you're modeling. So that's it for this first screencast for Bootcamp 3. The second screencast will look at a different type of reaction system that has different characteristics and presents different challenges for its solution. So we'll take a break here.